Okay, so we're going to start our calculus class. We're looking at in chapter 4, section 4.1, the minimum and maximum values in here. So as we start looking through the section, we see that we start off by discussing our absolute maximum and minimum. So if we look at that theorem here, it says that let f be defined on a set D containing C. If f of C is greater than or equal to f of x for every x in D, then f of C is an absolute maximum value of f on D. And if f of C is less than or equal to f of x for every x in D, then f of C is an absolute minimum value of f on D. An absolute extreme value is either an absolute maximum or absolute minimum. So basically what this is talking about is that we have our highest and lowest points on the graphs defined by an x input at x equals c value, then gives us an outcome value going on. So if we notice on the next page here, they have a couple graphs at which we're looking at. So we start talking about our absolute minimum value would be located at the vertex of this parabola. Here we have what looks like a half of a parabolic curve. So we see we have an absolute minimum, then we talk about that absolute maximum, and actually there is an absolute minimum here because we are not defined at this point. Over on here we have our absolute minimum, absolute maximum, and then on this one we talk about no absolute minimums, no absolute maximums, once again, because we see that they are open hold, or they are moving up to that point but are not existing at that given point. Okay, so do realize that as we start looking at these graphs, we see that we have no absolute maximum here, because even though this is a high point here and the point is defined, this other curve is higher than what it is over here, but it does not exist at that highest point, and then our absolute minimum will be that lowest point on the graph. So one of the easiest ways to look at these is by having our graph present for us. If we continue on in this section, we talk about the extreme value theorem. So in this extreme value theorem, talks about a function is continuous on closed interval from A to B, inclusive, has an absolute maximum value and an absolute minimum value on that interval. Okay, so in which then we'd be able to start locating these. Now do realize absolute maximums, absolute minimums are there, but we do have other points on here that are of critical values, in which then we start talking about local maximum and minimums. In the local maximum and minimums, we start looking at this theorem right here where we talk about, suppose C is an interior point on an interval I, of which f is defined. If f of C is greater than or equal to f of x for all x in interval I, then f of C is a local maximum value of f. And then the same thing follows as local minimums. If you notice, I have a little side note in my book right here, where it talks about local maximums and local minimum values are also called relative maximum and relative minimums. They're also the local extrema or local extreme, whether it's singular or plural. So what we start seeing here is we start seeing that as we start looking at points, we see that the slope of our secant lines, basically our tangent line within here, comes to the slope of 0. So that's where we start talking about our critical values. Okay, so when we start looking at critical points, we start talking about that the local extreme value theorem. If f has a local maximum or minimum value at C, then f prime of C exists, in which then f prime of C equals 0. So basically what we start doing here is we start taking the derivative of our function, in which then we'll set it equal to 0, and then we'll take all those existing points at which it equals 0, and then we'll start substituting those in to find which is our values at which we have here. And then we start talking about our critical point right here. An interior point C of the domain f at which C prime or f prime of C equals 0 or f prime of C fails to exist is called a critical point. So do realize that if we have any undefined values in here that we cannot take the derivative of, those are also critical values that we must note within. So as we kind of continue on, you can see right here, we see that even though we have f prime of C does not exist, we do have a local minimum value within here, and then remember on any corner or cusp the derivative also does not exist, but it does not mean that we will not have any local maximum, so we do have to pay attention to the types of curves that we're also working with. So basically some of the steps we start looking at as we're going through, we start looking at assume that the function f is continuous on the closed interval from a to b. Okay, so if we're continuous, we locate the critical point C in an open interval a to b where f prime of C equals 0 and f prime of C does not exist. These points are candidates for our absolute maxima and our absolute minima. Evaluate f at the critical points and then the endpoints of a and b. Okay, so we don't actually perform a derivative on the endpoints because remember our derivative has to have a right hand and left hand, in which then, because this is an open interval right here, we don't include a and b, but we do check the endpoints coming down here for absolute maximum minimum. And then we're going to choose the largest and smallest values of f, from which step 2 for the absolute maximum and absolute minima respectively would be. That brings us to our section at which we'll be discussing problems in the next video.